All right, so thanks for coming to the colloquium. It's my pleasure to introduce Eric Hudson, my colleague from UCLA. I asked him what I should say about him, and he said, "That's it." But I'm going to say more. Right, so Eric did his PhD work at JILA, working with Jun Ye on experiments involving the efforts to produce cold molecules. Went and did a postdoc at Yale University, working with Dave DeMille, and then moved to join the faculty at UCLA. Eric could tell us a lot about ultra-cold molecules, or at least cold molecules and trapped molecules, and some novel chemistry that they undergo, but I don't think that's what we're going to hear about. Eric could also tell us about innovations relevant to ion trapping and ion trap quantum computing. That's also not something he's going to tell us about. Eric could also be telling us about a phenomenal development at UCLA where he's together with colleagues, they've established a master's program in quantum science and engineering, one of the first in the country, and that's now gone through 2 successful years. He's not going to tell us about that. Instead, he's going to tell us about something having to do with optically driven nuclei, and I look forward to your talk.
Is this volume okay? Like this? Okay, perfect. That's really high. Okay, perfect. Well, thank you guys for the invitation. It's really great to be here. You'll see under all these affiliations, there's the Challenge Institute for Quantum Computation, which is this Berkeley-led center for quantum computing through the NSF. We're a part of that. And because of that, I actually kind of know my way around campus. It's starting to feel like a second home. So it's really fun to be here. What I want to use my time today is to tell you about this, what until very recently has been a crazy dream in our group for a very long time, and that is to perform laser spectroscopy on a nucleus. The outline is here. I'll start off by telling you the story of this nucleus, which is thorium-229, how since 1976, really more than 40 years, folks have been trying to do just this. I'll tell you about our efforts, which was to realize you could dope thorium into some high band gap crystals, and then I actually decided to take this out so I could focus on other things, but I will mention it because I think there's some maybe connections here, some experiments we did when this wasn't working, and then I'll come back to nuclear laser spectroscopy. And this work was funded over the years, not well, but but nonetheless not zero, by NSF, ARO, and DARPA. And we're really grateful for that funding. Okay, so as Dan said, my lab does several different things, and I like to call it our lab strategy and put it in air quotes because who knows if there's a strategy. But the thing that excites me, and maybe you'll see today, is getting control of new things at the quantum level. You could just generally do fun stuff whenever you bring a new system under, let's call it quantum control. There's work that I do with some quantum chemists, some regular chemists, and Wes Campbell, who many of you know is an atomic physicist at Berkeley, where we're taking what I sometimes say is the ultimate limit of nanofabrication. Right? The ultimate limit of nanofabrication is chemistry. Right? If you could build something atom by atom, then you can maybe build new devices. And maybe we should take that approach to building quantum hardware. It could maybe be defect-free. You could maybe make moles of it. You can use things like, molecules can move. They can photo-switch to bring about new interactions. And so this is a really fun and super crazy project that I never know where it's going, that I'm working on with these folks. With Wes Campbell, I also work on trapped ion quantum computing, so some of the things similar to what Hartmut is really leading here. We also work with molecular ions, trying to get control of them for all sorts of quantum things. And then the thing I'm going to talk about today is this nuclear clock. Okay. When I turn my head, is this microphone cutting in and out, or is it okay? Okay, it's weird up here. All right, so let's think about this picture. I think we're all pretty familiar with ChatGPT's version of an atom. We have some electrons orbiting a nucleus. Electronic structure, we know there's a 1/r potential. The protons are attracted to the electrons, and the electrons repel each other. We can solve this. We say there's these well-defined quantum numbers. These orbitals fill according to a Pauli exclusion principle, and we get all of atomic physics, chemistry, and most of the things that we know well. But, and the excitations are of order EV. So what about nuclear structure? Well, first of all, what is that potential? And so for the next part here, if you're a nuclear physicist, I apologize in advance. So Wick, just cover your eyes. Somebody covers his ears. For everybody else, this is exactly right. So let's think about nuclear structure, right? So we have a bunch of fermions. So we have two flavors of them now. They have some kinetic energy. There's up to 8 of them, right? And then there's some interaction potential between them. And how do we think about this? Well, it turns out the nuclear force is pretty short range. It's about the range of action is maybe something like the size of a lithium nucleus. And so what we could say is, let's just kind of replace this with some sort of mean field interaction, which is averaged over all these sort of short range interactions. And let's make now our Hamiltonian be. There's a part where it's a kinetic energy operator, this mean field, plus this bit over here, and we don't really want to think about it, so we'll call it the residual part of the Hamiltonian. And it's just the difference between our mean field and the true interaction. So if we then take the next step, we say, okay, what is this U? I don't know, most things are harmonic oscillators, so probably it's a harmonic oscillator. And so we can get pretty far with this. We just pick omega to reproduce the right energy levels. And we could find the energy levels of this nucleus. Now, in these sort of heavy nuclei that we're going to talk about, this residual interaction plays some role. And what it does is when you start to fill multiple levels, if you think about this, I haven't really talked about, I guess I should say, okay, you take this potential, what are you going to have? You're going to have some principal quantum number, and you're going to have orbital angular momentum, right? And so you could have shells that fill according to a Pauli exclusion principle. This residual Hamiltonian, one of the things it does is it's going to make you feel the M sub L levels not in the way you would in atomic physics, where you pair them up and so things stay symmetric. And so what you can get is actually a deformed nucleus. And we say, well, we can still treat that by just taking and deforming our harmonic oscillator. So we treat this potential as a deformed harmonic oscillator. Obviously, this thing goes to infinity at long range, and the nuclear forces don't. So this is an approximation, but it does quite well. And then you say, okay, well, I know my valence neutron here, let's say, in the case of thorium, also has some spin, so there's some spin-orbit coupling. I'm not writing down L and S here, because this is no longer spherically symmetric, it's cylindrically symmetric, so I use cylindrical quantum numbers. The good quantum numbers are projections onto the symmetry axis. If you know molecular spectroscopy, this is just like say, a Hund's case A molecule. And then the next correction we need is, well, the nuclear force is very short range. It's shorter range than this nucleus. And so this harmonic oscillator really isn't right. It should be a little bit flatter. Because when this thing is in the middle, there's as many nuclei over here as over here, and so there's no net force. Right? This is called an orbit-orbit interaction, and we can just add that in because higher angular momentum states are going to be further out, and there's going to be a correction here. So this together gives us what's called the Nielsen model. This is the principal quantum number. This is the number of quanta in this Z harmonic oscillator. This is the orbital angular momentum, and this is the total projection onto the symmetry axis. Okay, so we now see that we have, just like in atomic physics, these energy levels. We know they're going to fill according to a Pauli exclusion principle, right? And so we expect shells and all that goodness. So how do we measure that? Because I haven't said it yet, but all of you know that nuclear energy levels are very energetic, right? While atomic physics is sort of electron volt excitation, nuclei are kilo-electron volt or mega-electron volt. We don't really have lasers or light sources really in that regime. This is one of the beautiful things about nuclear physics is you get the spectroscopy for free. And so I'm going to walk you through an experiment that was done in 1976 that was the genesis of the story I'll tell you today. So some guys, Kroger and Reich at the Idaho lab, had uranium-233. That alpha decays, and when it does, it produces 229 thorium. Now, if you think about the nucleons in the uranium nucleus, they were perfectly happy being uranium. And now suddenly they're not. Right? And so they're no longer in the ground state of this new potential, this thorium potential. And so what do? They spit off gamma rays as they relax towards the ground state. And so if you collect these gamma rays, you can reconstruct the energy level structure of thorium. And so that's exactly what these guys did. And what they found is shown here approximately. It wasn't quite this good, but over the years it was refined to this. Here's the ground state, nuclear spin 5/2. You can see that these excitations are of order 40 keV, 97, same sort of thing over here. And they found that there was an excited state here that was incredibly low in energy by nuclear physics standard. You'll notice on these other labels, they don't even show the third decimal place, and that is where this is. So how do you think about this in terms of this earlier Nielsen model? Well, I like to think of it in terms of this valence neutron. We have this thorium nuclei. It has a total projection onto this nuclear spin axis of k equals 5/2. This state here is exactly the same thing, but it's the k equals 3/2 version, right? So you might look at this, and especially if you know molecular spectroscopy, you would say, hey, this looks like a doublet delta 5/2 and a doublet delta 3/2, like spin orbit split state. And you say, aha, I see now why this is only a few eV. This is a spin orbit splitting. In nuclear physics, spin orbit splitting can be MeV or maybe even more. So that is not what this is. Right? This is something else. It's evidently just a magic cancellation of what has to be the strong force and the electromagnetism, which is trying to push the nucleus apart. Right? And as far as I know, there's really no explanation of this other than this was just one of the flukes of the universe. Okay, so with this, people went to look for this transition. This was first pointed out, almost 50 years ago. In the 90s, people thought they found it for a while, and then those experiments were later proven to be incorrect. And eventually, things just sort of got quiet. And then in 2007, a really important measurement was done led by Livermore with Los Alamos and NASA Goddard. They effectively just redid this experiment, but they had better technology. And what they said is, oh, it's not 3.5 eV. It's about 8 eV, 7.8 eV. Now, for your nuclear physicist, who cares? Right? You notice like the eV digit isn't even on these graphs. But if you're the poor atomic physicist that were looking for this is the difference between a 300 and something nanometer photon and something in the vacuum ultraviolet. So none of the previous experiments could have worked because the photon they were trying to detect would, just doesn't propagate in air, right? Completely absorbed. And so this re-energized everyone to start looking for this again. And with these properties of the transition, so they didn't know the transition line width. This is, maybe I should say this in lifetime instead of line width for other people. It's, something like a couple thousand seconds was sort of the radiative lifetime of this transition. This is just sort of based on knowledge of nuclear physics and an estimate for what this was. But we knew that, hey, this is a very narrow transition, and this is a very high energy transition. So many atomic physicists got excited about this because if you give atomic physicists a wavelength and a lifetime or a transition width, the first thing they do is calculate the Q, the transition Q, and they say, this is an oscillator with an enormous Q, 10 to the 19 or so. And the higher the Q oscillator, the better clock you can make. And so a lot of people have thought about making this a clock over the years. And perhaps even more importantly, it is my suspicion for the long run, is that because this is a nucleus and not based on electrons like all other optical clocks, your systematic shifts are going to be a lot different and a lot smaller. BBR shifts are minimal. I mean, the first electric dipole transition's at like 40 keV, so that's pretty far away at room temperature. There's going to be small differential shifts just because the nucleus is small. So like the quadrupole moment, the nuclear magnetic moment, they're just all much smaller than what we normally deal with. So the first proposal that I know about that this could be useful for a clock actually came in 1996 from Moscow, from Eugene Tokalia, who pointed out basically these properties and said, wow, this could be a great clock. a couple years later, 7 years later, there's a paper that's very famous within our field from Eckert Pike and Christian Tam, which is really the first time that like atomic physicists really knew about this, I think. And also they did a very, a much more serious analysis of this, whereas Takalia is more of a passing comment. Sometime later, there was a result or a paper from Andrei Derivienko with Alex Kuzmich, which showed in sort of modern language, using modern technology, that you could build a clock of really state-of-the-art or better performance. And I think this got a lot of people excited. We got involved. This is actually Dan's graduate student, Wade. We got involved many years ago, earlier than this, because we were trying to solve a problem of how do you find this transition. And what we landed on was that you could take this thorium-229, dope it into a solid state, high bandgap insulator, and not only drive this transition, but make a clock that has performance better than the definition of the second. It won't be as good as the ultimate, like trapped ion or trapped atom clocks, but it's better than the cesium standard, and it's in a little crystal that you could put in your pocket. And so, the dream would be that you could take this NIST F1 clock, which keeps time for the nation when it works, and replace it with just some thorium-doped crystal. There's got to be some lasers, and we'll come back to that. But if I'm honest, as I alluded to, this wasn't the real reason that we started this research. The reason was we were trying to solve what I call the needle in the haystack problem, which was this was a very narrow line. Right? Estimates at the time were 10 to 100 microhertz. And the transition was known to be somewhere between 140 and 180 nanometers. So this is a very hard search problem. I used to call it actually the needle in the briar patch, if you know what a briar patch is, probably, because it's so hard to work here. And the idea of the crystal was that we can dope so much thorium into these crystals that even with, say, a synchrotron, like up on the hill, we can excite enough nuclei to see their fluorescence. And that's exactly what we set off to do. Because with using, say, the advanced light source, we could scan this 140 to 180 nanometer range in a couple of days. Whereas if we had to do it with a laser, it would take a few years. And so we set off to do this at the ALS. The problem, and this is why it took so long, 16 years, I guess, was that you need a lot of things that just didn't exist at the time. You need this crystal that would accept thorium as a dopant. Thorium's a big atom. Most things don't want it. It needs to be VUV transmissive, so it needs a really high band gap. You want it to be radiation resistant because thorium-229 has about an 8,000-year half-life. This is like fairly radioactive, and so you don't want this thing to be damaged by the thorium. And then you don't want it to glow from all the radioactivity inside of it, like the uranium dinner plates that glow in the dark. That would be bad because we're trying to excite a transition and see photons. So we worked for a very long time to try to meet these. Another problem was we thought at a minimum a couple milligrams of thorium-229. You would think that's not that much, but the very first quote we got was $6 million. Yeah. Luckily, they gave us 60 days to think about it. But nonetheless, after some time and begging and pleading, Oak Ridge really helped us out. We got about 3 milligrams of thorium-229 from them. I thought about trying to sell it on the black market and retire, if I'm honest. Couldn't find a buyer, so we stayed with the project. And then we worked for about 5 years to be able to survey what we thought were the best crystals and then learn to grow them and dope them with thorium. So it's about 5 years of work to produce these little guys, which to me are roughly priceless. They have 10 to the 17 to 10 to the 16 thorium-229 atoms doped into them. They're transmissive down to about at least 140 nanometers, and they are stable, which was something we were very worried about. And I want to thank two people. Syed Mirzadeh, who was a radiochemist at Oak Ridge, who the whole field already owes and will continue to owe a great debt to. He had the foresight to extract thorium-229 when he could and save it for the right experiments to come along so that it didn't get wasted. And Hans Jensen, who is an absolute wizard of crystal growth. So there's no way we could have done this without him. So these guys are really, really important to the story. All right, so we had the first crystals made, I guess, around this time. I think our first batch was maybe a little before this. And we went up to the advanced light source on the hill. This is the ALS beamline. It's beamline 9. If you know that one, it's the chemical dynamics beamline. And this is our experiment. So what we have here is there was the crystal inside of this little chamber. There's 2 PMTs on either side, and there was some shutters. So we would just shoot the ALS VUV beam in to try to excite the thorium. Then we'd shutter this beam, open these shutters, and just count photons. This is like the simplest experiment you could imagine to look for this. I will tell this story, actually, because maybe somebody's here, and it will do some good. When we got this run here, we didn't know if the crystals were going to survive or not. Like they were the first real batch of radioactive crystals, and we didn't know if they would just decompose in a day or a couple of weeks. So they basically come out of the oven, they're polished almost while they're still hot, drop them in the envelope, and ship them to the ALS. We also brought a thorium-232 crystal to the ALS. So thorium-232 is the regular thorium. It doesn't have this nuclear transition. And the idea was this was our control crystal, that if we see something in the 229 crystal, we'll drop in the 232 and it should go away. And so when you ship these crystals in, you have to ship them to the radiation receiving department. They check that you're not telling lies about what you get, and then they bring them to you at the beam line. And it's pretty late by the time we're getting ready to drop them in. And I just said to the guys, it's like, what's the chances that they flip the crystals when they unpack them? And my grad students are tired, and they're like, there's no way, these guys are professionals, that would never happen. And I somehow, for whatever reason, I was just like, no, we're not doing it. You guys got to find a Geiger counter, and we got to figure it out. And sure enough, they had flipped the crystals. So you should always check. In the end, it didn't matter, because at this experiment we didn't see anything in either crystal, but it's still good to check. All right, and so this was our limit plot, or our exclusion plot, we called it. So on this axis is the possible wavelength. Here's 140 to 180 nanometers. On this axis is the lifetime. This blue region is sort of where we thought this should be with what I would say 90% confidence. And that's, it's kind of hard to say a confidence interval when you're putting together a lot of different experiments, but it's like a reasonable kind of estimate of the transition should be there. This is something we did with Eugene Takalia in Moscow. And so we didn't see anything, and we could produce an exclusion. So the red region is the area that we could exclude at roughly a 90% confidence interval. So we took a big bite out of this parameter space. We couldn't go here because the ALS, they just weren't allowed to tune it there anymore. And we couldn't go up because we just needed more flux. The ALS makes a lot of photons, but its line width is quite broad. When you're driving a transition, that's like a millihertz wide, right? In the crystal, it's broader than that, but still, it's a very narrow transition with a broad source. So what did we do? We went back to UCLA and said, I guess we have to build that laser. So that 3 to 4 year search, we're just going to have to do it. So we took a laser. It's based on 4-wave mixing of a couple pulse dye lasers. There's a cell of xenon here where some VUV light is made. And it comes to the same chamber we used at the advanced light source. And it's exactly the same idea, just to shine a laser on, turn it off, and look for fluorescence. It couldn't be simpler. The problem was that we would have to run for 24/7 almost for like 3 years. And so these pulse dye lasers can be very finicky, and so we had to work quite hard to automate the system. And I really want to thank Christian Schneider, who's now at JPL, and Justin Jeet, who's now at Livermore, who really spearheaded this effort. They had to develop VUV power monitoring. Turns out that people would sell you VUV power detectors, like pulse energy detectors, but you would plug them in and they would give negative power because they never actually used them and thought about photoelectrons, so we had to solve a lot of problems. I had to do all kinds of frequency monitoring and locking. And we also had to record in real time the pulse spectrum. So this is a pulse laser, if it goes multi-mode right as you go over this narrow transition and you miss it, you really want to know that, because it takes 3 years to scan this. You can't do it really twice. This was complicated by the fact that, as I alluded to earlier, the project was not well funded because it was thought to be crazy in certain circles. And so we had to dig these lasers out of the basement of a chemistry department and refurbish them. And they're so old that they were manufactured in West Germany. They're actually really good lasers if you take care of them, though. So I'm a big fan of these lasers. All right. And so then about once an hour, because the lifetime is like, 2,000 seconds, that's a good fraction of an hour. You get a data point an hour. We would get an email from the experiment, and it would look like this. You don't need to know what these are. We're just like things about the wavelength, things about the power, things about the pulse spectrum. And then this is really the plot I mostly looked at. This is the number of photons in the first 1,000 seconds after we turn off the laser, and you hope to see exponential decay here, right? And so we did this scan for 3 to 4 years, and we saw nothing. And if you put this exclusion, we excluded at a really high level all the way down to about 147 nanometers. So what's going on? So this was a few years ago, and so we started to get worried that this approach wouldn't work. And here's why we were worried. I say no obvious long lifetime signal. So we didn't see any fluorescence that had a 1,000-second lifetime or even a few 100-second lifetime. But we did see some fluorescence that had a few second lifetime. And what that looks like, if you look at what we call the short lifetime signal, the total amount of photons in, say, the first 50 seconds, it looks like this. From 184 down to about 160, we see nothing. This is like 2 years of just zero every day. Then around 8 eV, we saw a little bump. But then we put in our thorium-232 crystal, the one that doesn't have the nuclear transition, and we also see a little bump there, so we're not too worried about it. Maybe it's a defect associated with thorium, or maybe it's an impurity, because you could have a little bit. This is not a huge signal, a little oxygen or something in the crystal. And then as we got down to around 8.3, 8.4 eV, we started to see this short lifetime signal going up and up and up, and we just couldn't really tune our lasers past here without a lot of modification. And so we stopped there. And if you zoom in here, we then put in another thorium-229 crystal, and we saw a similar behavior. That's this black curve. Whereas the 232 really didn't show anything here at the level of our signal to noise. And so the question that we started to worry about is like, okay, maybe the nuclear transition is somewhere around here, and maybe somehow the crystal is quenching it. And we're getting just a much faster, broadened thing instead of this beautiful narrow line we had hoped for. So Anastasia Alexandrova is a quantum chemist at UCLA. She's fantastic. Her postdoc, Harry, took this on. He's now starting a faculty position in the UK in a few weeks. And they did a really amazing calculation. So this is 4x4x2 unit cells of our crystal. So this is lithium, strontium, aluminum fluoride is our crystal. This red guy is one thorium doped into this. You have to do these big unit cells because the way the boundary conditions in these DFT calculations work, if you just tried to do the unit cell with one thorium in it, you would just have a thorium everywhere, the way the calculation runs with sort of periodic boundary conditions. And so this is about as big as you can go with sort of supercomputers that we have access to. There's like 2,000 electrons here. It's a crazy calculation. And what they calculated are shown here. So this is the density of states calculation. So if you're not used to thinking about that, let me walk you through it. On this axis, it's basically the number of states per EV. And this is energy. But this is not just the regular density of states. This is the density of states projected onto thorium-centered orbitals. So these are the thorium sp, d, and f. And I'm picking these because I want to show you something in a minute. If you include, say, the fluorines in the crystal, they have there's way more way more states on the fluorines there. So what we see here, this is the valence band. This is the top of the valence band. Here's the conduction band. This is about a 10 eV band gap crystal. Right here are defect states associated with the thorium. You dope a thorium into the crystal, it has to change a little bit to accommodate it. Some extra fluorines come in. And so these are excitations associated with the thorium, and they have sort of mostly F character and a little bit of D. Now, here is the nuclear energy if I just draw it on here. This is where we saw this sort of region. It's about right here. And so what we got worried about was that and I should say we worked with Andrei Derivienko, who's amazing, and his postdoc BAO. We started thinking about how the hyperfine interaction between the electrons and the nuclei could couple the 2 degrees of freedom and could potentially lead to this quenching. So that, there are many ways that this could happen, but generically, it's something like this. Suppose I have an excited nucleus. It's about this much energy. If it's coupled to the electrons, it could give energy to them. And it could resonantly excite an electron down here. It needs to be a thorium-centered electron to really talk to it, up into this defect state. And if it does that, this hole that's left behind will quickly quench to the top of the band. This happens in like picoseconds because the phonons shoot out and this relaxes. On a shorter time scale, nanoseconds or longer, maybe even seconds, this will then relax by photon emission. And if it does, it should make a red-shifted fluorescence because you have to excite from below band to be resonant with this. So we said, okay, if this is true, let's go look for it. And Ricky and James were the grad students working on this. We didn't have enough signal to really put this into a spectrometer, so they basically took every filter we could get and just took different combinations and then did a Gaussian deconvolution and backed out the spectrum mathematically. And what we found was this blue trace here. Red of 225 nanometers, this is just the phosphorescence of the crystal. We already knew this. You could just take the crystal, put it in a grating spectrometer, and integrate. And the crystal glows a little bit in the UV because it's radioactive. But what they then saw was a very narrow peak, somewhere around 180 nanometers, which is right around where the DFT calculation is. So we, at this point in time, were starting to think, hey, this idea that we've been pursuing for over a decade will just never work. That generically you're going to have these defect states, there's going to be this quenching, and this whole crystal approach won't work. Around that time, actually, let me see, how much time do we have? Do we go for like an hour, or is it a little less? Okay, yeah, that's good. I never know with Berkeley time. It's always confusing. Okay. I'm always like, oh shit, we're out of time. All right, so something important had happened around this time that I want to mention. So in the lab of Peter Thyrolf in Munich, he had taken uranium-233, like this experiment I mentioned earlier. When it decays, it produces thorium-229. If this is a thin coating, it can get ejected from the surface. They have a quadrupole mass spectrometer. They can just select each thorium, some thorium ion, and they were soft landing it onto a microchannel plate. Now, when you do that, you have some ion, maybe it's say thorium 3+ or something. You land it on this microchannel plate, and it neutralizes. When it does, the binding energy of this electron, the ionization potential, is actually less than the nuclear energy. So the nucleus can relax by giving its energy to this electron, and the electron shoots off. And so the MCP will actually click in that case. And so you land the thorium on this, you get a click, and then 10 microseconds later, it should click again. And so they saw this, and it confirmed, really, in my mind, it confirmed the nuclear state existed. Like before this, which was not that long ago, a lot of people didn't believe the state even existed. And it also told us that this IC process worked. So we set off to do 2 experiments because we thought, okay, the crystal approach isn't going to work. I won't talk about them in detail. I'll just say that there's an experiment where it's very similar to the crystal approach, except it's effectively a thorium metal as the target. And the idea is that you can get enough light into the first little bit to excite some nuclei. They will then emit these electrons, these internal conversion electrons with a 10 microsecond delay, and you can see the transition. And if you run the numbers on the line width, it could still be of order tens of kilohertz. and then maybe this is actually a really good clock, and you don't have to collect photons, you collect electrons. And so this is still an active area of research. This is a collaboration with these folks. We also had a really nice collaboration with Sai-Wu Nam, who unfortunately, you may know him, recently passed away. It's a huge loss to the community, and Galen O'Neill with some superconducting nanowire detectors. And so we were off in this world. And then last year, something really important happened. Piet van Dupen at Leuven University did a crazy experiment. This was so crazy, I know people in the field who turned down being a part of the collaboration, but it totally worked. It's the best kind of experiment. And what he did was take like calcium fluoride or magnesium fluoride, like some high band gap optical material, and at CERN, in the Asalda facility, implanted actinium-229 into them. Actinium-229 will beta decay into thorium-229. And the choice of actinium over something like uranium, which is what people had done before, was brilliant, I think. When uranium decays into thorium-229, it's an alpha decay, and it just wrecks the crystal. But a beta decay is a much softer thing. And so what he then saw was if he took these samples after he placed actinium in them and some of them convert to thorium, when they convert to thorium, there's a decent fraction that convert to the excited nuclear state as the gammas just rain down. And so then he just looked to see if any VUV photons came off of the crystal. And sure enough, they saw a few nanometer wide signal around 150 nanometers. And more importantly, they saw a long lifetime. They saw that this was like maybe 1,000 seconds. So what was interesting to us is that this is exactly where we saw this thing shoot up. But what was not interesting, or what was surprising to us, is they saw a long lifetime. So for a while, we were thinking, okay, maybe there's something about calcium fluoride that doesn't quench these crystals, whereas this nuclear transition, while the LISAF does. And so we were thinking about these things. But luckily, a few months after this paper came out, Peter Thyroff, who I mentioned earlier, was visiting us at UCLA. We said, hey, Peter, here's some LISAF. Sneak this in your carry-on. When you get back to Europe, convince Pete to put this in the beamline and see if it works. And the beamline schedules worked out wonderfully. And a few months later, Sandro, the grad student who's leading the whole thing, emailed us and said, hey, guys, your crystal works too. But probably not all of it. And so this was a key realization for us. Because I had previously thought, well, if there's some quenching, like, I mean, it might be like maybe 1 in 10 to the 8 isn't quenched or something. Like the signal's sort of hopeless. If there's a little bit of quenching, it's probably all quenched, right? But they were saying, maybe it's a few percent actually survive and actually emit photons. And so this exclusion that I gave you, you have to pick something. So we always just said this assumes 100% thorium participation. So all the thorium in the crystal would contribute to the signal. If it's a percent, these move down by like 2 orders of magnitude. And so now some blue region is now allowed. So we said, okay, let's reanalyze this data differently. And this gray region is sort of where Pete said the transition should be. We said, okay, over this gray region, I don't care about if we saw anything or not. I just want to know how many photons did we see total in the 1,000 seconds after we excited. And so that's what's shown here over about a nanometer. And we said, okay, this is the total number of photons we detected after excitation. And just for to guide the eye, calculate the mean and then draw the mean plus standard deviation plus 2 standard deviations, right? This is not something you're gonna make any statistical claims on, so we're just trying to figure out, were there any points that were interesting? And you see there's sort of 5 points here that were more than 2 sigma fluctuation from the mean, not that surprising over 100 points. But there was one point, the highest point here was almost 3 sigma. And so when we went back to that point, what we saw was a tiny little bump that was about 10 gigahertz wide, which is the width of our laser. And so we saw a little signal there. We've never seen anything like this anywhere else. Then we said, okay, well, if this is thorium-229, let's put in the thorium-232 crystal. And we don't see anything here. Now, that's exciting, but maybe not the it doesn't have to be the nuclear transition. It could still be some sort of weird defect, even though although this is really narrow already for a defect. Let's put in another 229 crystal. And we grabbed a crystal off the shelf which had less thorium in it. And we saw a much bigger signal. It turns out that the crystal we had been using for all these years, only about 1% of the thorium participated. But we had 3 other crystals on the shelf. And in all 3 of those crystals, about half of the thorium-229. So we chose the wrong crystal 4 years ago. I don't know. It's just, that's what you do when sometimes things aren't easy. And so this is pretty exciting. It looks like the nuclear transition. Perhaps we were then able to really drill down on the frequency. It's 202407 gigahertz. I'll remember that number hopefully forever. We can then go here and measure the lifetime, this long lifetime. We see something about 570 seconds. We've measured this better now, and it's about 570. I had said earlier that we would expect this thing should be a couple thousand seconds. I've sort of left out something important. In the crystal, the index of refraction is not 1, and so the photon density of states is larger by n cubed, the index of refraction. And since this is a magnetic dipole transition, the magnetic field isn't changed in the dielectric, so overall the decay rate is enhanced by n cubed. So this would mean that the bare lifetime, or the lifetime of the nucleus, is about 2,000 seconds, about where we expected it. The issue is we don't exactly know the index of refraction of this material. We're working with NIST right now to measure it. Our supply of LISAF was in the path of Helene, and we haven't heard from them in a while, so hopefully things are okay. All right, so you may know that Ecker and Pike, using crystals grown by Thorsten Schum, also saw this transition. Their paper actually came out a couple weeks before ours, and they measured something at 409 gigahertz, a little bit larger error bar, and a similar lifetime. And again, the lifetimes don't have to be the same because this is a different material. They were using calcium fluoride. And so, this question of, is this really the nuclear transition? We have similar lifetimes, the same wavelength within error bars in completely different hosts. I think we can be confident now that this is really the transition. Now you might be saying, well, why didn't you think that already? You saw a narrow line, you saw it in 229 and not in 232. The truth is, 232 doped crystals are not chemically identical to 229 doped crystals. When they're made, they are. But the 229 is radioactive. It has an 8,000-year half-life. The 232's half-life is the age of the universe. So these crystals have been sitting there getting bombarded with alpha particles and all the daughters and all the bad things that can happen. And so, it's conceivable that maybe you make some sort of color center or something in it that has a really narrow line width. But I think now that you have it in 2 different hosts, you can be really confident in this. But of course, the world's not enough. As soon as you find this, even though we've been looking for it for literally, personally, 16 years, the next thing is, what's the line width? How narrow is this transition? And there, a few months later, Junyi had a VUV frequency cone, which you can't really use for this. It's not what we use for these original searches because it's got to be a very robust laser that works all the time. But now that you know the transition, you can park this thing here. And what he saw was the individual states. So the ground state is I5 halves, the excited state is nuclear spin 3 halves. The crystal has an electric field gradient, and the nucleus has a quadrupole, so the levels are split by the quadrupole, so they split by the absolute value of M. And you expect 5 transitions. Actually, 6 is actually allowed by mixing, but they observed 5 of them. And the line width that they see is a few hundred kilohertz, and from their experiments, that's their laser. That's not actually the transition yet. So we don't actually know what the line width is yet. And everybody is working on narrowing their line widths to address this. And what's kind of crazy about this is, as I was putting this talk together, I stumbled on this. This is a poster I gave when I was a postdoc. So I had this idea as a postdoc, and I was working for Dave, and Dave is awesome if you don't know him. I was like, hey, I got this crazy idea. And he's like, that's great. I have this money over here. I don't know what it's for. You could have it. Just go do stuff, right? He's like, fantastic guy. This is a poster I gave at the ICAP of Monday, July 28th. You can see this is 5th of September, not bad. 2008, 2024. And in this poster, I drew this diagram. I was like, this is what we'll see someday in like a couple of years. So sometimes you got to be foolhardy to do physics, I think. I don't know. Okay, so we have the nuclear transition. What's next? Now, the crystals that we picked for a lot of good reasons. But now that we know the transition, we can start to get creative and think, how can we do this better, right? The problem is, it's still, crystal growth is a very long development cycle. You know, it can take years to perfect growing a crystal, and then you start to grow thorium into there, and like the people that really know how to grow crystals well are all retiring. It's really kind of a bad situation. You know, there are problems we want to fix, like the thorium doping fraction, like thorium doesn't go into these crystals, evidently there is some quenching, like how can we make this better? So there's one thing that we're doing, and this is a recent paper we did with Pete, who I mentioned earlier, and his student Sky, who led it, where we went back to Salda, this beamline facility, and just put a bunch of different things in to see if we could see these photons come out as sort of a scouting experiment. If you see a photon come out, then that crystal will work, is my claim right now. And we see our crystal, some other crystals. We put in some things that shouldn't work, and they didn't work. And so the next round, hopefully, we'll get to explore more. But, you know, CERN is shutting down this, or ISALDA will only probably have one more run of this, and then we won't get to do it again for a while. So we got to be creative. And a crystal that we've always wanted to use was thorium fluoride. Because if you dope thorium into thorium fluoride, there's no defect. So the gap stays empty, right? There are none of these like wonky states in the middle that could be problematic. We didn't do it because if you go to the Materials Project webpage and you look up thorium fluoride, it tells you the band gap's 6.5 EV. So it's just not transparent in the VUV. However, a couple of years ago, mostly from what I can tell, led by Richard Martin, some people reevaluated this. They did new DFT calculations that led to experiments, and the band gap's actually 10 EV. It's not 6.5 EV. If you talk to DFT people, they're like, yeah, sure, that sounds right. But for us, that's a really big deal. So we would love to do this. This could solve a lot of problems. But growing a thorium fluoride crystal is a lot of work. So we just so happened, within this thorium metal collaboration, the way this worked, we had been coating, say, stainless steel with thorium oxide, thorium fluoride, and we were getting these made commercially. But Lars von de Winter, who actually led Peter's IC experiment, moved to June's lab and became a postdoc there, and they were doing this metal search as well. And Lars said, you know, the stuff we're buying, it just isn't good enough. I think we're going to have to make these samples ourselves. So he built a physical vapor deposition system at Gila, where they take the radioactive thorium, heat it up, and just like spew it onto different substrates. And so June's grad student now, who inherited this, Chong Kuhn, once we found the transition, said, hey, I can make you guys a thorium fluoride thin film. And we're like, okay, we'll try it. That's crazy. It's not a crystal. It's going to be polycrystalline and probably all quenched, but might as well try. So Chong Kuhn made it in a few hours. He coated thorium fluoride on some sapphire and on mag fluoride, and this is what it looks like. This is like, say, a sapphire, a little window, and there's maybe 100 nanometers of thorium fluoride on there. FedEx will ship anything, so they took this, and 24 hours, we had it in our lab. Literally 24 hours later, we had it, and Ricky and James took the laser, put it through to collect fluorescence, and we saw this stupid transition in this thorium thin film, which like honestly kind of made me mad a little bit, because this is just like some crap sprayed onto a substrate. But when you take a step back, I think this is a really good sign for the field. We can see this even in crazy things. Now you will notice that the signal to noise is terrible here, and the participation fraction, the amount of thorium that should contribute, that actually does, that ratio is less than 1/10%. Right. Well, that probably sounds reasonable for such a thin film. The lifetime is also shorter in this sample. We expect it to be a little shorter because of the index of refraction, but not a full factor of 4, so that's a little bit of a mystery. When we do this on the mag fluoride substrate, we see the same thing. The signal to noise is better because the mag fluoride doesn't scintillate as much from the radioactivity, right? But a similar lifetime. And so I think what's really exciting about this is the young folks may not know, but thorium fluoride used to be a coating for optics, like an AR coating or mirror coating. Like, this is a review article written about thorium fluoride films and all the cool stuff you can do with them. It was a review article in 1968, right? So humanity's pretty good at working with thorium fluoride. So where I'm really excited about going with this is making waveguides, incorporating thorium fluoride into like a Bragg mirror. Like, there are all kinds of really cool things you can imagine for making a deployable clock where the optics are built into this thing. I also think that there's going to be a whole industry that springs up around this because things like strain are going to affect the nuclear transition, temperature is going to affect it. So I think there's going to be some really new sensors that come out of this as well. So this paper. So, the thing that has paid the bills is this idea of a portable clock, that you have this crystal, I could hand it to you and you could take it home and build a nuclear clock. This looks very portable, right? That's a penny. This is still the size of the room, right? Our laser is ginormous. You can't really put this on a satellite. It also needs a small power plant, right, to keep it in the air. So what do you want to do? Well, now that we know the wavelength, we can start thinking about nonlinear optics. And there are a handful of nonlinear materials where you could imagine producing this light. And I'll pick this first one because it is one that I think is closest to being triable. So this barium magnesium fluoride, you can do quasi-phase matching and double to produce 148. So that sounds great. You have a 296 nanometer laser, you double it, and then you can interrogate your crystal. But if you think about it for a second, you realize, why do I need this crystal? Why don't I just dope the thorium into here? So I can generate the VUV light and interrogate the thorium in the same crystal. Harry has done the calculations, and at the level we understand why LISAF works, the one we use, this should work. And this is actually a really big deal, not just because it makes the lasers easier, but I no longer need vacuum, right? The 148 nanometers is never in air. It's only ever produced in the crystal. And so now all I need is a 296 nanometer light laser, and that's pretty easy. Right? I can get some double whatever and get there. So we're really excited about pushing that down. All right, so I'll stop there because I think I'm out of time. I told you about the long story of getting here, some nuclear laser spectroscopy, and then where we're going in the future. Thank you guys for your attention.
Thanks, Eric. Are there questions?
How do you calculate the participation fractions, and why are they not 100%?
So it is a hard measurement because you have to understand your detection efficiencies very, very well. We've done calibrating things like solid angle of collection are hard, but we've worked on that for a number of years. And I would think we know it to better than a factor of 2. So that 50% could be 100. That 1% is not. We know how much thorium is there. That's easy because it's radioactive. You just take a gamma ray detector and you can see a thorium line, and you know with really high precision the number of thorium atoms that are there.
Maybe if you'll allow me, I guess what I'm wondering is sort of in the crystal, what is happening? It's making some of the thorium participate and some of it not.
Well, that's the question of the day. My suspicion is, so I gave you this story about these defect states and this quenching. If those defect states, we're working on calculating what that quenching fraction is, because those defect states really should be there. And you can work out in perturbation theory what that rate should be. And there's something we don't know, which as a molecular physicist, I would call it the Frank Condon factor, if you know what that is, the nuclei change upon excitation. It turns out if you ask a DFT person this question, their head explodes. They have, there's like a few people that know how to calculate it, but it's not clear, like, to get quantitative numbers seems to be like state of the art. So we don't know that number, but my suspicion is that it's very low and that these defect states don't really quench it. The quenching we're seeing is that there's an impurity or some dislocation in the crystal, and it's a weird site that's quenching. And that these states are more resonant or something's different. But we don't really know right now. The sample size is like 2.
So I was curious down the same line. What does the participation fraction in the thin films tell you about this whole picture?
Yeah, it's a really interesting question. I mean, the problem is we don't know that much about the thin films. We know that they're polycrystalline, but it's hard to know like what the impurity levels are and all that. My suspicion is that these things are 100 nanometers thick or so. That's less than the wavelength. So if there's like hydrocarbons or something on the surface, and there are, then that you can couple to those degrees of freedom and quench. That would be my guess, but I think it's, all you could say right now is almost emotional kind of thing. It's like, it's a dirtier system, and it is therefore worse.
So maybe you can clean it up a little.
Yeah, so one of the things we're going to do is try to anneal these things and see how they, what I can say is that these thin films that we made, over the course of a few weeks to a month, the participation factor got even lower.
Al. So I guess to play the devil's advocate, so in rare earth ions, for example, if you look at inner shell transitions, they're electronic transitions, but they're screened from the junk.
Right, yeah, they're like F to F transitions or
F
something.
to F
Yeah.
transitions. And I mean, in cryogenics, you can get down to kilohertz levels.
Right, yeah,
and
exactly,
even
yeah.
at room temperature, I think you could get to gigahertz.
I don't think I've seen any at gigahertz at room temperature. Maybe.
But like, I guess, how would you kind of say that this is not one of those?
Not a color center. I think the VUV cone measurement is the best because we see exactly the hyperfine structure you expect, right? And the intensities of lines is dead on.
Is that at the same frequency?
Yeah, it's exactly. I was very happy that ours is 2024-07.3, and June's measurement picks up to the 3 and just keeps going. Yeah.
Dan.
I was reading that sapphire fluorescence around, or phosphorus is around 80 dB. Is that, you mentioned this discrepancy earlier in the signal, the sapphire versus the others.
So the sapphire definitely has a lot more background than the mag fluoride, but that is part of that is roughly constant if temperature of things are constant, like those background rates don't fluctuate too much. And so this is on top of that background. So it's why the sapphire data was not as pretty as the mag fluoride data, but it shouldn't show up in this asymmetry. I mean, it just makes it noisier. It can't, I don't think it can bias it.
Holger.
So this is a wonderful result, and it was worth every second of the 15 years it took to get it, right?
I had hair when we started. I don't know.
When you have to submit your tenure this year after 5 years, so which aspect of the way science is done enables a person to do science like that?
That's a really hard question. What I will say is this, like, in the US, thorium was not well funded, but it was funded. There were program managers out there who said, I believe in this, it's crazy, we're gonna keep you going. They're not gonna give you a lot, but they kept us going, right? I think that was important. The NSF was always there when we were in trouble, because that's, I'm really thankful to them for stepping in at times. And then I think our community was very supportive. I mean, I kind of got sick of being asked, have you found it yet? Like, that was the question at DAMOP, but I don't know. I mean, it could be better, but it could be worse, if that's a good answer.
That's a really cheerful note to end on.